It's a pleasure to be here. So I'm going to talk about BICEP2 results, implications, and future of tensor cosmology. The subtitle of this talk is, it's really an amazing combination of three big ideas, theoretical ideas: inflation itself, and how inflation generates gravitational waves, and how gravitational waves get detected by generating B-mode polarization in the microwave background. And also, in combination with amazing technology and dedicated experimental programs. And some human element, focus, teamwork, faith, etc. So another amazing thing is we get to do all of this at the South Pole, one of the most exotic places on the planet. Here's a picture of our neighbor, South Pole Telescope. You can't quite see our small experiment next to it, but it's doing much bigger science than the big sister. You can see Aurora here and the Milky Way. So the basic experimental approach is, you heard about cosmic microwave background as the most ancient light. But if you want to study inflation, it's not ancient enough, because cosmic microwave background is also a curtain blocking the very beginning. The surface of last gathering was at 400,000 years old, when the universe was at 400,000 years old. So you need something that can travel across the entire universe to study the very beginning. And that is a gravitational wave. So we use gravitational wave to study the beginning, or inflation. And photons, you can't quite do that, because it's a wall of radiation coming at you when the universe was already not that young. So the approach is to, so this is kind of a wall blocking, everything before 400,000 years old from our view. And but gravitational wave can just travel across that opaque, hot, ionized medium. So the question is, how do you detect gravitational wave? Well, the nice thing is gravitational wave leaves a very distinct imprint in the polarization state of microwave background. And that's how you do it. So gravitational wave leaving an imprint in microwave background. And this is what we observe. So we're looking at an image of gravitational wave imprinted on microwave background. And that gravitational wave was generated directly at the bang of Big Bang, or inflation. By the way, this is now the official BICEP2 version of the history of the universe that you should feel free to copy and ditch the W map and Planck one. So the first big idea is inflation. So inflation was proposed in late 70s and early 80s to solve a few classical cosmological problems. Many of you have heard of it, and I'll just give you one example here, and that is the horizon problem. So basically, why was the universe started out so uniform, even though they didn't have time, different regions didn't have time to talk to each other and get into equilibrium. So if you trace the trajectory of a test particle, in this case a galaxy, you realize the horizon size, which grows as c times the age of the universe, c being the speed of light, grows linearly. And if you trace to earlier and earlier time, all of this stuff will be, basically coming into the horizon, okay? Meaning at early time, these regions didn't have time to really talk to each other. And yet, when they appear on the horizon, they appear to be uniform. So different regions look the same. So the way inflation solved it is to move all these trajectories below the horizon scale at the beginning, all right? So this is how you do it. And now all of a sudden, there was time for different regions to thermalize and appear the same, basically. So this is how inflation solved the horizon problem. In other words, if you look in, this is still time, so the scale of the universe has to undergo a rapid expansion, all right? So this is a very rapid expansion because time is this way. So inflation solved the horizon problem by resorting to exponential expansion of space. So you probably heard of that, but if you just hear about it today, it takes a little thinking to understand that. It's a very difficult concept. So how is it achieved? So many of you have seen this equation. This is the famous Einstein equation for gravitation. But if you haven't seen it, it's okay, because it's completely analogous to the Newtonian version, the Poisson equation, where phi is the gravitational potential and rho is the matter distribution, the density. And this is just that. So in Newtonian limit, this reduces to that. This is the general relativistic version of it. So if you take the energy of a scalar field, it seems foreign, but it's exactly the energy of a spring, if you think of it this way. In fact, it's completely identical to the energy of a spring, okay? And if you take the energy of the spring and you calculate the tension, and so on, the kinetic energy and all of that, and you plug into the right-hand side of the Einstein equation, you get exactly an exponential expansion. So it's just as simple as that. It's completely classical. So as long as you have such an object, a scalar field with a pretty generic energy form, you have inflation. Okay, so there's no quantum mechanics or anything like that. It's just classical field theory with gravitation. So if the scalar field changes very slowly, or it satisfies the so-called slow row condition, you get a constant expansion rate, or A dot over A, the Hubble parameter. And that gives you a constant exponent, and it's an exponential expansion that solves this problem. All right? So it's a very simple concept. You only use general relativity, basically. And what you get is the energy scale of your string or scalar field gives you the expansion rate. All right. In addition to solving the classical cosmological problem, inflation does a very nice thing. It generates perturbations. Okay, and this is the part that we talked about, a connection, deep connection between quantum mechanics and the cosmos. Okay, and prior to BICEP2 results, the properties of the scalar perturbation, this is one of the two types of perturbations generated by inflation, became the strongest evidence for inflation, actually, because people started to question the naturalness of how inflation solved the flatness and horizon problem and so on. Okay, so in the end, it was the property of the perturbation that really gave inflation very strong support before BICEP2 results. So these properties are, so the perturbation, because it it's entirely coming from a single scalar field. It has to have only 1 degree of freedom, or it's an adiabatic type of perturbation. All different components fluctuate the same way. And the fluctuation has to be Gaussian distributed. And the spectral index is close to scale invariant. So these are the pillars of inflation, if you will, before the gravitational waves were detected. So this is a schematic view of how fluctuations were generated by inflation. Even in vacuum, during inflation, the uncertainty principle demands that there is 0 point fluctuation, okay, in all the fields. So the fluctuation in the inflaton field itself gets inflated and amplified, if you will, to create the density perturbations discovered by Kobe and very well studied by Planck, WMAP, SPT, and galaxy surveys and so on. It became the seed of structural formation, and that grows, the fluctuation grows under gravitational instability, creating clusters of galaxies, planet, people, animals, so on. So that part is very well known. So another part that's very well theoretically motivated is the vacuum fluctuation of gravitation itself, or if you will, the ground state of graviton. Okay? So if gravity is quantized, there will be vacuum fluctuation in graviton. And that part will be inflated and amplified, just like the inflaton field was. And it creates a gravitational wave background. And we believe we just detected this gravitational wave background. So by doing so, we completed the inflation paradigm, and we set the energy scale of inflation, okay, at the grand unification scale. A little bit of more physics, because this is a physics fulcrum. So if you take that Einstein equation and you linearize it, so you've done this in classical mechanics, and you get a harmonic oscillator. And in this case, it's very similar to harmonic oscillators, except for the expansion term, okay? Without the expansion term, it looks just like a harmonic oscillator. It gives you a plane wave solution. So there are 2 types of plane waves, so these are very complicated tensors, right? So you get one scalar type perturbation, and you get a tensor perturbation, which is a gravitational wave. So the form of the solution looks like this. So without looking at this part, it's just very similar to plane wave, but in an expanding universe. However, with the expansion term, when for a given scale, okay, when that scale gets beyond the horizon scale, perturbation becomes frozen. The amplitude of the perturbation becomes frozen. So this is a very simple linear solution to the linearized Einstein equation under the simple inflation background. Okay, so it's all classical mechanics, all classical physics again. There's no quantum mechanics or anything like that. However, for a given field with a plane wave solution, if you combine that solution with uncertainty principle, you know the expectation value of that plane wave cannot be 0. All right? So the RMS value for that for that plane wave is assigned by Heisenberg's uncertainty principle. So likewise, combining this linear solution with uncertainty principle, you fix the RMS, or the expectation value of the linear solution. Otherwise, the amplitude of the linear solution could have been 0, okay, for both the inflaton field and the graviton field. But in this case, it's, there's an h bar attached to the amplitude of both. So this is a very distinct prediction of inflation, and it just comes from the simple fact that you attach an amplitude to a linearized solution for both inflaton and gravitons. So I think this is one of the most important calculation in physics. It's really blowing my mind, just the combination of GR and quantum mechanics. And these are the people who did this work. So these people did the scalar part, and these primarily Russian did the gravitational wave calculation, which turned out to be very similar to the scalar, in fact simpler than scalar calculation. But my student could have done this now with Mathematica, very easily. They didn't have Mathematica. All right, so understanding that part, you can understand why this is kind of a big deal, because this gravitational wave started out as graviton vacuum fluctuations. So if gravity is completely classical, you wouldn't have this. So gravity has to be quantized to begin with. And then the amplitude of this fluctuation tells you the energy scale of inflation, because you evaluate this frozen amplitude at horizon axis, and that's related to the Hubble expansion. Okay? So energy scale of inflation is expansion rate during inflation, and it's the gravitational wave amplitude. So once you detect it, you set the energy scale of inflation. So alternative models tend not to generate any gravitational wave. If it did, it tend to generate very blue spectrum. And the high frequency end is severely constrained by direct gravitational wave probes. So the low frequency end is pretty much 0. Okay. So you can just remember this. So alternative models tend to generate no gravitational waves. And string theorists are all excited about the field range of inflaton, which I won't get into, perhaps some other time. But there's a deep connection between the amplitude of gravitational wave and the symmetry property in quantum gravity. When you're trying to, create a quantum gravity theory from scratch, for example, using string theory. So that's very nice. So there's density perturbation, there's gravitational wave fluctuation, but how do you tell the difference between the two? So after early 80s, people thought this would be impossible, because gravitational wave also generate temperature fluctuation in the microwave background, just like the density perturbation. So after 15 years, several smart theorists finally figured out a way to do it. So they realized the linear polarization state in the microwave background can be decomposed into E mode and B mode. So E mode has no curl, and B mode has no gradient. Okay, just like any arbitrary three-dimensional vector field can be linearly decomposed to two such fields. One looked like electric field, one looks like a magnetic field. And likewise, linear polarization pattern on the sky had similar properties. You can understand that. So the two patterns had different parity. Okay, so E mode had even parity, and B mode had odd parity. So my undergraduate student at Stanford created this app. All right. So what's going on is we're looking at a screen of ionized plasma, free electrons, if you will. And the polarization was generated by Thomson scattering, or just the E&M wave moving the electron, back and forth and re-emitting polarized light. And as you can imagine, if you have a point source unpolarized at the center of the circle, the polarization pattern will look like this, because outgoing wave would tend to move the electron only this way. So when the wave was re-emitted, it's polarized in this direction, okay? And if you make a circle out of it, it's polarized in this direction, this direction, this direction. It becomes an E-mode polarization, just like what I defined as E-mode. Okay, so the nice thing is, whatever you do, however many point sources you have, you're not going to create a curl, a B-mode polarization pattern, okay? And if you can't do it with point sources, you can't do it, period, because you can create any function with point sources. Okay? So now, that means any linear density fluctuation generate zero B-mode polarization, or the curl polarization. How about gravitational wave? So if you recall, gravitational waves have two polarization. One is a plus pattern, it stretches space this way and this way. And one is cross, stretches space this way and this way. So this is a gravitational wave propagating toward our circle of electrons with polarization, with cross polarization. And again, you generate E-mode. If you change the polarization state of the gravitational wave, you get B-mode. Okay? So to summarize, any linear density perturbation can only generate E-mode. And gravitational waves generate both E-mode and B-mode. In other words, if you look at this B-mode, this curl, you're looking at only gravitational wave, not the density perturbation. So this is a nice property proposed by those gentlemen in 97. So that's very nice, but the polarization pattern is still very small, even though it's unique, okay? So how small? So the vertical versus horizontal power is different by 1 part in 30 million, okay? So that's almost by definition an unpolarized light, but it's, this is called B-mode polarization for some reason, even though it's too small to be called polarization, really. But this is the tough task. Okay, so you need very sensitive detectors, and you integrate for a very, very long time to see the difference between the two. And also, you have to deal with systematics. You can't measure the vertical power for a while and then look at the horizontal power, for another an hour, and you subtract the two, and you get junk. So you have to do, several layers of modulation, if you will, and make sure you know what the instrument is doing. So sensitivity and systematics are the big challenges for an experiment like this. But we're talking about difference in power for vertical and horizontal by 1 part in 30 million. That's why we justify our experiment to be at the South Pole. Because it's actually the driest place on Earth because of combination of low temperature and high elevation. It's actually at roughly 3,000 meter altitude. It's extremely cold. All the water vapor in the atmosphere is frozen on the ground, so there's very little left in the air. And water vapor is a big microwave emitter as well as absorber. So you go to South Pole to do this experiment. Also, there's 1 day and 1 night per year, so you get to have very stable climate for continuous observation for 6 months. There's also very good logistical support from US NSF Office of Polar Programs. We use C-130 military flights, these planes on skis to go to South Pole with plenty of leg room. Lots of important experiments were done there. The 10-meter South Pole telescope. This is where we had BICEP1, BICEP2, and soon BICEP3 later this year. And DAISY, the experiment first detected EMO polarization, quad, and now Keck. All right, so the technology part. So how do you measure the polarization difference in 1 part in 30 million? So the nice thing about searching for B mode, gravitational wave generated B mode, is you don't need very big telescopes because the predicted angular scale is around a degree or a few degrees. And at microwave frequency, that corresponds to 20 centimeter telescopes, not 20 meter telescope, for example. So you can, in fact, put the entire telescope in a dewar, like we did in the BICEP series, BICEP 1, 2, 3, and Keck. All these experiments are part of a very focused program to look for gravitational wave. Okay, different generations of it. I'll get into those. But all of these use cold refractive telescopes. BICEP 1, BICEP 2, and Keck had 25 centimeter aperture. BICEP 3 gets to about 60 centimeters, but still very compact. But these are all cold telescopes at 4 Kelvin, liquid helium temperature, and the detectors are cooled to a quarter Kelvin. And for the later generation, for BICEP 2 and Keck series, we have fully lithographic detectors with mass-produced tiles, silicon tiles, and I'll show some of that. But the optics is very simple. It's just 2 lenses and a focal plane with lots of detectors. And that's all we do. It's also very similar to a condensed matter low temperature experiment, if you will, except when we finish it, we ship it to South Pole when we start observing. Also, we need to have a big window to emit microwave radiation. We can't just block it off and let the sample get cold. We have to open it up to the ambient radiation, hundreds of watts, and yet keeping the detectors cold. So there are lots of challenges in there. So all these experiments, different acronyms, are only after one thing, that is R. So R is the tensor to scalar ratio, measuring the amplitude of gravitational wave with respect to scalar perturbation. And they all look like this, okay? So this is an extremely focused, a big gamble, if you will, for multiple groups. So the first experiment in this series, BICEP 1, uses more conventional phi-horn coupled detectors, hand assembled by grad students. I'll show some pictures. But later on, BICEP 2, Keck Array, and BICEP 3 uses lithographic planar antennas. They look like this. So there's scale there, 3 millimeters. So what you're looking at are vertical and horizontal slots. After all, this is a polarization experiment, right? And the voltage difference generated by incident microwave, okay, was collected by this meandering summing tree coherently and then sent to a on-chip filter, and then that power is dumped onto a thermally isolated thermometer. Okay, so these are thin legs, okay? And the bolometer or the thermometer heats up as you scan back and forth. And if you do the subtraction, there's another detector here collecting the horizontal polarization. I don't remember which one goes to where, even though I designed it. But you know the idea. You take the difference of the 2 detectors, you scan, and you do complicated math to form a map. So the nice thing is this is all completely lithographic. You can make lots and lots of detectors. So this is my notebook. When I first realized this can be done back in 2006, when we were developing BICEP 2 detectors, when BICEP 1 is still running. So like I said, this is a very, very focused program. Even though BICEP 1 is still just started observing, we're already developing technology for BICEP2 and so on. And this is very hard work, so I have to motivate myself by thinking about inflation all the time while I was calculating the impedance of these microstrip lines. So the detector looks like this. So the microwave coming from the telescope and that complicated antenna gets sent to this island. This is just black, it's just empty space. So this is really thermally isolated from the bath. Okay, so this thing heats up, but not here, not this part. Okay, so this is a very sensitive thermometer. And that wave is converted to heat in here because this is a lossy resistor, if you will. And it heats up, and there is a superconducting thin film thermometer located here to convert the heat signal into a current signal. And the reason to use superconductor is that it's a very sensitive thermometer. You change the temperature slightly, the resistance changes a lot. Okay. And here's a gorgeous picture of BICEP2 focal plane under the microscope showing the bolometer and the slots and that crazy summing tree. And after that development, for the past 8 years, we fabricated more than 100 tiles of these things, all looking for gravitational wave. Okay. So this is the first generation BICEP1 focal plane. Like I said, all hand assembled by a grad student. And after we've gone to lithographic detectors, we can pack a lot more of them. So, so BICEP2 was 10 times faster in sensitivity to R than BICEP1. And now BICEP3 will be 10 times faster than BICEP2. And we will really be able to follow up BICEP2 results with BICEP3. This is the size of the collaboration. It's not, very small, but it's not very big either. So your voice can be heard. If you have good ideas, you can implement it and it'll be respected. So it's a very good size collaboration. I really enjoyed it. Lots of talented people. This is what work is like at the South Pole. Lab, it's very well maintained facility. Room temperature, as you can tell, in the lab. Outside it's cold, but you can do most of the lab work at room temperature. A pair of hands showing the size of a BICEP2 type receiver. Not very big, but with lots of detectors, very sensitive. So not only is our program very focused, but also our telescope, okay? So it goes on and on. So BICEP1 did this for 3 years, then BICEP2 did this for another 3 years. And what you're looking at is Keck, which is an array of BICEP2 type receivers. And it's been doing this since 2011, so 2.5 years now. So we're just scanning back and forth, taking the difference between two polarization states, making a map. And that little funny thing you probably noticed was a calibration. Oh, there we go. Because the atmosphere is not polarized. So you do a little dip, and you use that to calibrate the gain of two polarization states. So this will get boring if you keep watching. So, but that's the point. So we're all very focused. So this is BICEP2 data. The Q map, U map, and this is the depth measured in nanokelvin. Now it's going to second year. and you start to see pattern in QMAP and UMAP. In QMAP, you see these plus patterns, and in UMAP, you see these cross patterns, because the polarization state is dominated by emo polarization. Okay. And if you take, this is what we call jackknife tests. So you take the first half of Q and you subtract it. The second half of Q, from it you get the difference, and you should see nothing except for noise. And that's what we did. So we just saw, just this jackknife maps are just consistent with noise, and there's real signal emerging from the unjackknife test maps. So if you use polarization vectors, and this is what we got after 3 years. So there's definitely polarization detected in BICEP2 field, and it's mostly E mode, if you remember the definition of E being radial pattern or circular pattern around a point, right? So you don't see, there's no big curl jumping at you with this map. Again, so the scale of this is 1.7 microkelvin. That's tiny compared to 3 Kelvin of microwave, of CMB, of microwave background temperature, and 30 Kelvin of our total instrument loading, including the atmosphere. Okay, so it's mostly E mode. So remember this circular pattern around it. So if you use a nice mathematical trick that involves linear algebra by solving a gigantic eigenvalue problem, you can get rid of all the E mode and leaving only B mode. Okay, so from here to here is a matrix operation that I learned from this department actually 20 years ago. So I did learn something. All right, so if you zoom in, okay, this and this are the same thing, just different scale. I just blew up the scale by a factor of 7 or something, 6. And this is all curl, because by definition, after that matrix operation, there's only curl left. Okay, so it's not a big surprise that you only see curl. But the nice thing is, the noise level is way below this level. Okay, even if you operate noise map, even if you use matrix operation on the noise, completely noise map, you get completely curl, only curl out of it. But the nice thing is, our noise level is way below this level. Okay, so if you had a simulation with noise level consistent with our map, the level is way smaller. So we believe nearly all of this is real on the sky. So if you plot the scalar of that curl mode or B mode, you get something like this. Okay. So if you turn this into a spectrum, into a power spectrum, okay, it's just a measurement of amplitude versus angular scale. This way being small angular scale, that way is large angular scale. This is about 1 degree, this is about 2 degrees. Okay. So the solid points were the BICEP2 points. Okay. The error bar is very small compared to the detected signal. So again, we believe nearly all of this is real on the sky. And when you do a jackknife, meaning when you split the data in 2 halves and you take the difference, no matter how you split the data, in time, in different observation angle, the telescope was doing this scan, and you form a map from left-going scans versus right-going scans. However you do it, the signal is gone. Okay, so if there's systematics, you expect some of these jackknives will fail, but we found nothing. So we're really convinced this signal is on the sky. So we came up with 14 different jackknives, and all of them pass the consistency check. So that took a year. So when this first showed up, I mean, there's no way this is real in the sky, come on. But then, we exhausted all the possibilities. We have to publish, and we believe this signal is really on the sky. And after, we've done that, we compare the BICEP2 data in solid points with Keck data, cross-correlate with BICEP2, and also with BICEP1 data, cross-correlate with BICEP2. So remember, BICEP1 was the previous generation, and Keck was the next generation, which was a copy of BICEP2. And again, we pretty much saw the same thing, with some fluctuation. Okay, but the important message is we've seen something, and if you plot a inflationary curve plus lensing generated B mode, and it's an excellent fit to the data. All right. So these are the different consistency jackknives tests we've done. This is a whole year of work. We're trying to be very creative in how we split the data. So the most challenging jackknife was done with different, what we call bore side rotations. So our telescopes are small, or in this case, the BICEP2 telescope is very small, so you can afford to rotate the entire instrument. And if there's any systematic effect in your instrument, it rotates with the telescope, but the sky signal remains the same. So it's a very tough test to pass, and yet we passed that. We have different bore side rotation jackknife tests, and we all passed that. So again, we're really confident that there's no way this is related to the instrument itself. How about astronomical foreground? You have to look through the galaxy after all to see the microwave background. So we have some color information, but the main message is it's really unlikely that the level of the signal we observe can be explained by foreground. Most likely dust. Dust will be the dominant foreground at our frequency. So the level of dust polarization has to be huge in order to explain our data, which gets really unphysical. Okay, so we think that level of dust contamination is around 10% or smaller than the level we detected. So if you add the sample variance, which is coming from the fact we only measure a few modes in our map, this is our bottom line power spectrum plot. So the error bars are kind of big, but these are all sample variance limited. So string theorists, they only care about this plot. You can wake up now, take a look at this plot. So we detected a largish tensor to scalar ratio at 0.2 with some error dominated by uncertainty dominated by just sample variance. But the main message is the null model, null hypothesis is ruled out at very high significance. So the likelihood is vanishingly small at 0, okay? It's not 100% certain that all of this is tensor. Maybe a small part of it is coming from foreground or not, or whatnot. But we don't think so. We think the dominant signal is really, the simplistic explanation is it's coming from primordial B modes, which provides an excellent fit to our data. Okay. These are the prior experiments, all trying to do the same thing. Okay. This is the gravitational lensing contribution from B mode. All right. So before we published, there was upper limits coming from indirect measurement with temperature fluctuation, temperature anisotropy from Planck, WMAP, combination with ground-based experiments like ACT and SPT, and the expected range of tensor is given by these curves, these contours, and this is what we found. So people make a big deal out of the apparent tension, but it's really at 3 sigma level, and that will probably go away. Remember, we are still limited by sample variance, so I wouldn't be shocked if it ended up being here or here. And, you know, I don't know what's going to happen with Planck, but it's 3 sigma tension. It will be really interesting if, you know, after a few years when we shrink the error bar, comes out to be here, then the tension it becomes real and hard to, you know, then you have to come up with an explanation why there is a tension. But so far, it's only 3 sigma. So the main message is, again, these models were ruled out. These low R models were ruled out with high significance. So, and many of these models were motivated by string theories. So implications, if our interpretation is correct, that the B mode we observe is dominated by gravitational wave, primordial B mode, then these are the implications. So inflation happened, gravity is quantized, and inflation happened at the grand unification scale, and chaotic inflation models, the polynomial type potential are favored. And many string motivated models have been ruled out. And many were pretty good looking models. And also the inflation field has to move, or the inflaton has to move over super Planckian range. And the implication is it needs symmetry in the ultimately unified quantum gravity theory. So the string theorists are very excited about this. There are lots of other implications. For example, half of the axion dark matter parameter space is ruled out, and many more. Okay. From what I heard, it takes a few years to sort out the theoretical implications of this discovery. All right. So we've gone too fast, almost, because we built BICEP1 and we observed for 3 years. And then we developed technology for later generation. And the first experiment of that generation discovered B modes, while the later generations have been funded and built. So we're in excellent shape to follow up this signal, really, and to shrink the error bar of it. And after we published our data, we really realized we're really far ahead of our competitors. So the latest upgrade of this program is called BICEP3, which is being built by my group at Stanford primarily. It'll just add another 2,000 plus detectors at a different frequency than BICEP2. And it'll cover more sky with extended frequency coverage. We can really conclusively say this is cosmological and with reduced error bars. So what was the technology development that made BICEP3 possible? So BICEP3 was a telescope that's twice as big in aperture as BICEP2, and that creates all sorts of cryogenic challenges by a factor of 4, basically, because the window size is much bigger, you know, and if you just use the same window, it implodes under vacuum, and the amount of ambient radiation coming in, you know, it's quadrupled because of the aperture, so you have to reject more of it. But we've overcame all that challenges, and BICEP3 is on schedule to deploy later this year. to start at least 2 years of observation, also from the South Pole. So this is the infrared filter we developed for BICEP3. I can explain what's going on here. You know, we were doing all sorts of fun things with technology, kind of low tech compared to the lithographic detectors. I can tell you more if you're interested. This is the lens material. It's high density alumina, ceramic. It looks opaque in optical, but it's completely transparent in microwave, which is a good thing. Has high index of refraction, and you have to anti-reflection coat it. And the material that you use for anti-reflection coating has different coefficient for thermal expansion. So you have to dice it using high power laser. Okay, so you know it goes on and on, but very fun, very interesting projects. And we, for some reason, I think we use more physics than high energy physicists. You have to know thermodynamics, you have to know mechanics, you have to understand resonances, E&M, optics, not just mathematics. All right. I think it's been a great ride for us. So what happens after BICEP2? Isn't this the holy grail? And you know, after you grab the holy grail, it's done. Well, you want to measure the amplitude to better and better precision. And given how big the gravitational wave amplitude is, we're quickly sample variance limited with BICEP2 and Keck. So we just realized the 2 years of Keck data with 5 times BICEP2 receivers, we're just looking at the same thing over and over again. It's a great confirmation, but it doesn't reduce the error bar in R. So BICEP3 and Keck next year, we're definitely going to cover more sky, but only to an extent from South Pole. Because you're at the South Pole, you can't really dip below certain elevation, which happens to be declination at the South Pole. So you have to go to a mid-latitude site like Chile to cover more sky. Okay, so after BICEP3, we're definitely going to Chile and other mid-latitude sites to increase the sky coverage. So this is a new proposal called the tensor experiment, or tensor. It's kind of childish. It's kind of my son's project, but at least the tensor experiment part is appropriate because we're trying to characterize tensor to greater precision. So we want to not only measure the amplitude but to better precision, we want to measure the scale invariance, the angular dependence. If inflation really happened, it really ought to be scale invariant, okay? And we want to measure the 3-point function. You know, if you cover more sky, you can do it. And if you have a good theory that predict a different 3-point function for tensor, please publish your paper before we measure it. Since we developed BICEP3, this straight duplication is a shovel-ready project. Okay, so we just need, you know, more of the same thing to cover a larger patch of the sky. So there's great opportunity. It's low-hanging fruit, and it's very low risk. So that's what I'm pushing. And the science return is unbelievable. Okay, just imagine shrinking the error bar of BICEP2 by a factor of 3 or 4. You know, you're really picking out, you know, which of these models is the right one. Okay, and right now it could be any of these. Okay, phi cube, you know, axiom, monodromy, and so on. These are the postdocs and grad students, and the winter over for BICEP2 across 4 or 5 institutes in the US. All right, I'll stop here and take questions.